So, good day class. Good day viewers and to all my students out there. So, we will discuss a new chapter which is compressibility of soil. Okay, I hope you see it. So, for compressibility of soil, this is synonymously the same to settlement. Okay, so the theoretical background is that the increase in stress caused by foundation and other loads compresses a soil layer. And because of this compression of soil layer, okay, the first one will be, there will be the formation of soil particle, and there will be relocation of soil particles. And the last one will be, there will be expulsion of water or air from the void spaces. Okay, can you see it? So these three are the major factors, or the reason why there is compression. But of course, compression alone is come from the loads, okay, of the building. And because of these three, there will be a settlement. Okay, so here there will be, of course, remember, in a soil particle, okay, considering a soil particle, it will have a voids and solid soil particles. Okay, and these voids can be water or air. Okay, so the first thing, or when compression happen, it happens because there is the formation of soil particle. Okay, and secondly, there will be relocation of soil particle, meaning here when we talk about the soil particle deformation, meaning the soil itself deform. Okay, deform uh, based on the load. Okay, and for the relocation of soil particles, remember, considering a container having a voids, no, considering different material, let's say these are the solid particle, solid soil, and these are the void spaces. Okay, so when there is a load, okay, of course, some of the solid particle may move from one point to another point, and because of that, there will be a deformation. Okay, and the last one is the expulsion of water or air. So this is a continuous process of the second one. Okay, because there is a relocation, there is also relocation of water or air, wherein some air, if this is the voids, okay, this may be air or water, so there will be some expulsion. Okay, expulsion. Okay, so these are the cause of compression. Okay, these three are the cause of compression. Okay, compression takes place because of these three. Okay, so let's continue. Let's go to the soil settlement. So, soil settlement will be divided into three. Okay, the first one will be the immediate. And the second one will be the primary consolidation. And the last one will be the secondary. Okay? So the first one is this settlement is caused by the elastic deformation. Elastic deformation, whether it is dry, whether it is moist, or saturated. Okay? Without changing the moisture content. Okay? So, this immediate settlement is caused by the elastic deformation, whether it is dry, moist, and saturated. When we talk about elastic deformation, we can say that when the load is removed, of course, it will return to its original size and shape. Okay? So, immediate settlement is the deformation of any types of soil without changing the moisture content, because once there is already changing moisture content, there will be already the volume change. Okay, so another one is the primary caused by volume change in saturated cohesive soil due to expulsion of water that occupies the void spaces. Okay, what happened here in the primary is, for example, you have a container and you have solid soil and you have void spaces. There will be expulsion of water that occupies. So remember that these voids, okay, the black mark, these voids, it can be air or water, but most probably more on water. Okay, more on water. So what will happen is, because of the load that applies here, some water inside of it will be removed, or there will be expulsion. Okay, this happens because of the cohesive soil. Okay, remember when we talk about cohesive soil, it has the ability to group into one. Okay, so meaning all the soil solid will be together and some water will be out of the container, out of the picture. Okay, and of course that in that scenario there will be volume changes. Okay, and the last one is the secondary is caused by plastic adjustment of soil fabrics. So this is additional form of compression that occurs at constant effective stress. Okay? So secondary consolidation settlement happens when there is already plastic adjustment of soil particles. So if we look at it with the category, o categories of the soil settlement, this is the last. Okay? So, secondary is already a form wherein there is already called the plastic adjustment. And this plastic adjustment refers when the soil cannot retain to its original shape. Okay? So, there will be an adjustment. How will be, what will be the interaction or, interaction of the soil when there is already expulsion of the water. Okay? So, do you have any questions? So, I hope you understand it, the theoretical concept. So, we can now proceed to the basic settlement formula. Okay? So, what is this all about? The basic settlement formula. This is the foundation on how we have the formula for the primary consolidation. So, we can draw here a sample that will represent, okay, this one. And we have here another. Okay. So, this is in the original state. And we have also here the compressed state. Okay? So, of course, you have here voids. You have here solids. And this one refers to, this is height of solid. This is height of voids. Right? And, of course, when there is, in compressed state, there will be the difference between the two, and we can call it as delta H. Again, this is voids, and this is solids. Okay, this is again the H or the height of voids prime, because it's already the new height of solid. Okay, so what we can notice here is that, remember that void ratio E is actually, what is the formula of E? Height of voids over height of solid. So we can say that height of voids is equal to E times height of solid. Okay? So now, we can notice that the total height here, the total height is actually height of voids plus height of solid. Okay? Wherein, height of voids is this one. E, height of solid plus height of solid, which is H is equal to height of solid times 1 plus E. Okay? Whereas, if you consider this value of H here, this is now called H prime. So, H prime is actually H prime B plus HS. Okay? And of course, height of voids prime is equal to E prime times height of solid. So, E prime because you have new void of ratio based on the diagram. Okay? So, the total height now will become H prime is, H prime B is E H prime plus, solid Can you see it? Okay, just I'm checking if it is clear. So H prime is HS times 1 plus E prime. Okay? So now, you have two equations derived. So from this figure, what can we notice? What is this delta, delta H? This delta H is actually total H minus H prime. Okay? And delta H is H minus HS times 1 plus E prime. Right? But, if we notice, and we can equate the value of HS. So here, H prime is HS times 1 plus E prime. Okay? H prime is equal to this. What is this value? Based on that, it will be H over 1 plus E multiplied plus 1 is E prime. Correct? Because here, this one is actually HS is equal to H over 1 plus E. Okay? This is the term that I substituted here. Okay? So, H prime is equal to H over 1 plus E times 1 plus E prime. Okay? What else? So, delta H is equal to H minus this one is H 1 plus E. Or you can factor H times 1 plus E minus H times 1 plus E prime over 1 plus E. Okay? Which delta H is actually H plus HE minus H minus H E prime over 1 plus E. Cancel this one. Delta H is H E minus H E prime over 1 plus E, which we can now conclude that delta H is actually H times E minus E bar over 1 plus E. And sometimes this E minus E prime is sometimes it is called the delta E. Okay? Can you see it? So now, the final formula for this is delta H is equal to H times delta E over 1 plus E. Okay, can you see it? Yeah. So this is now the formula for the delta H. Okay? So where H, this H is the height of the stratum. Then the E here is the void ratio per the vertical load or the original, and A prime is the final or the void ratio after the vertical load is applied. So this is the general term on how to determine the delta H or the settlement. Okay? So now we will move to the subtopic of this one. Can I move it? Okay. So now we will go to the different empirical formula that can be used for the consolidation settlement. The first one here, we have the primary consolidation settlement. The first one is for normal consolidated okay. So the formula to be used there, or the settlement, is the delta H. Can you see it? Okay. The delta H is equal to H times CC over 1 plus EO times log of PF over PO. Okay. In Bra MDAS, if I'm not mistaken, this is SP is equal to H times CC over 1 plus EO log of PO log of delta sigma O plus delta sigma O over delta sigma O, then this is delta sigma prime. Okay, for this is Bra MDAS. Okay. So you can use either of the two. By the way, the value of PF here is actually PO plus change of P. Okay. So this is for normal consolidated. Okay. H is the height of the stratum. CC is compression index. EO is the initial void ratio. PF is the sum of PO plus change of P. PO is the initial vertical effective soil stress, and PO is the initial and PF is the final, and PF is PO plus change of P. By the way, what is this PO? This is the this is the initial vertical effective stress. Okay? And what else? The value of change of P, it can be overburden pressure, or it can be sometimes called surcharge. Okay? Can you see it? Nice. So now, we have another formula which is for over consolidated. So here, you need to identify whether PF is less than PC. Where PC is this is called pre-consolidation pressure. Okay? So for this case, when the value of PF is less than PC, you can use delta H is equal to HCS over 1 plus EO log of PF over PO. But when PF is more than PC, delta H will become HCS over 1 plus EO PC over PO plus, can you see it? It's not visible anymore. Plus HCC over 1 plus EO log of PF over PC. Okay? So, these two formula is needed when you are comparing these two and if we are in over consolidated. So, again, for CS, it will be swell index and everything will be the same with normal consolidated. Okay? So, most of the time, we assume that the value of CC is 0.009 times LL minus 10%. But of course, in some other books, it depends on the situation. Because this assumption is only for undisturbed clay. Okay, undisturbed clay. So, what else? These are the settlement for primary. We have also settlement from secondary. Consolidation. By the way, class, don't be confused with the formula or with the term used here because now I'm just using the book of De La Senya, but for Bra-M-DAS it's the same, only the use of the terms or the use of the constant. Okay? That's why I mentioned a while ago that for Bra-M-DAS it's like this, but everything, I mean the definition of each term is the same, only the term itself is different. Okay? But the definition will be the same. So for the settlement of secondary consolidation, this happens when there is complete primary consolidation. And usually, the final time to attain the primary consolidation will become the initial time for the secondary settlement. Okay? And the formula to be used there is delta H for secondary is C prime alpha H log of T2 over T1. So, T2 will be the time after the completion of primary settlement where settlement is required, and T1 is the time for completion of primary settlement. T1 is the time for completion of primary, and T2 is the time the completion after the secondary settlement. Okay? So, C prime alpha is CC over 1 plus EP, where EP is called the void ratio at the end. Void ratio at the end of primary consolidation. Okay? And also C alpha, this is C alpha. C alpha is delta E over log of T2 minus log of T1. So these are the formula to be used. Then we have also the immediate settlement. For immediate settlement, you can use this one. Is equal to the pressure times the width or the diameter of foundation minus, times 1 minus mu squared over E times IF. This is net pressure. This is the width or diameter of foundation. This U is the Poisson's ratio. E is the modulus of elasticity. And IF is called the influence factor. Okay? And for influence factor, you can use the formula IF 1 over pi multiplied by M1 ln of 1 plus square root of 1 plus M1 squared over M1 plus ln of M1 plus square root of 1 plus M1 squared. So this is for the influence factor. But of course, for M1, it depends on the type of foundation. If it is circle or rectangular, then if it is center, corner, or rigid. Okay? Can we proceed? How many minutes we have? 32 minutes. So we will proceed, So what I'm discussing now is only the the empirical formula and the what do you call this one? The concept, okay? So we have also here the time rate. Time rate of consolidation. So for the time rate, the time t required to achieve a certain degree of consolidation U is evaluated as a function of the shortest drainage path within the compressible zone HDR, coefficient of consolidation CB, and the dimensionless factor TV. So the time T is equal to TV multiplied by the height of the drainage, quantity squared over CB. So what is this TV? TV is the dimensionless time factor, and HDR is the height of the drainage. And remember that for HDR is equal to 1/2 of the height if two-way drainage. And HDR is equal to H if there is only top or bottom. Okay? So this T is the time required to achieve certain degree of consolidation U. Okay? So, we have different ways on how to determine the value of TB. We have here, for example, we have the approximate value of TB. So, it depends if U or the consolidation is 0 to 60%, you can use TB is pi over 4 times U in percent over 100 raised squared. Okay? Or if U is more than 60%, TB is 1.781 minus 0.933 log of 100 minus U percent. So, the time factor TB provides a useful expression to estimate the settlement in the field from the result of laboratory consolidation. So, we have a direct calculation on how to determine the time required to attain a certain degree of consolidation, whether we are in the lab or in the laboratory. So, we have here T field over T lab is equal to HDR field squared over HDR lab. Okay, or we can have here T1 over T2 is equal to U1 squared over U2 squared. T is the time required to attain degree of consolidation, and U is actually, this U is the same with this one. These are the degree of consolidation. Okay? So we have also the coefficient of consolidation. For coefficient of consolidation, we have the root time method, which is CB is 0.848 times HDR squared over T at 90. Okay, then we have also the log time method. CB is 0.197 times HDR squared over T at 50. Okay? Of course, you can determine the value of T. The time, the T90 and the T50, here is the time for 90% consolidation. Okay? Based on the square root of T curve. Then T50 is the time for 50% consolidation based on logarithmic T curve. Okay? Any question? My God! If there's no question, we will proceed. So the other one is the coefficient of volume, compressibility, which is called MB. So MB is equal to AB over 1 plus E average, where AB is actually EO minus E over change of P. So, EO minus E over change of P over 1 plus E average. While E average is equal to E plus EO over 2. Then we have also K, which is CB times MB times gamma of water, which is called the hydraulic conductivity. Okay? Of the layer for the loading range. Okay? So if you do not have any questions, we will now proceed to problems. Okay? But of course, we will cut from this video because it's very difficult to upload the video with more than 40 minutes already. So thank you guys for listening. So wait for further videos for the sample problems. Okay? Thank you.